Thank you very much. Good morning, everyone. First, I would like to thank the translators, and I would thank all of you for listening to me in English, and I apologize to the translators if I speak too quickly, but I typically have a lot of material, so you should never ask a professor to give a lecture and put a time limit, because it's always a problem. So what I want to talk to you this morning about is the outcomes of some research I've been conducting in the situation with performance-based building regulations and fire safety engineering in different countries. And so I'll talk a little bit about what a performance code is and how it's different than a prescriptive code. And then I'll go through a few different countries and some of the challenges that those countries have with their regulatory system and with fire safety engineering. So building regulation and fire regulation generally has developed out of the health and safety area because we were very good at burning down cities 100 years ago. So somebody decided maybe we should put in some regulations to try to control for that. And so we instituted a number of measures like limiting the heights of buildings, the areas, compartment size, try to make access easy for the fire service, define how large compartments should be, fire resistance, and we kept adding all of this regulation, and we very much specified everything that needed to occur. The problem is, in many countries, not all buildings fit that very tight prescription, and it can be difficult to innovate in the design when the regulations are very restrictive. So starting around 1980, there was a movement to transition to what they call performance-based codes. And the idea here is that the regulation focuses on the societal goals like safety in case of fire. You define a functional requirement, something like provide adequate means of escape given the fire protection systems in the building, and then you put operative requirements such that the fire safety systems in the building shall be designed to maintain a tenable environment for the time that it takes people to evacuate. So very clear statements of purpose with some criteria that you're trying to judge, and then you have means to verify through engineering analysis, but then you also have examples of acceptable solutions, which in many cases are what used to be or are still called the prescriptive codes. And you can see a difference, for example, in the United States, the International Building Code is very prescriptive, 623 pages of text to tell you exactly how many meters to an exit, what the fire resistance is, and it works very well if the building looks like a square box no higher than 4 stories. But with very unique designs, it's very difficult. In England and Wales, the regulation is only 19 pages. It basically just tells you that make the building safe. And so we can do engineered design by exception in the US, but in the UK, it's permitted by law. And so both sets of regulations are very much underpinned by clear standards for testing of materials, design, and so forth. But it's really an issue of, do you start from telling everybody exactly what they have to do and then allow exceptions, or allow people to do whatever they want and have most people default to the very specific guidance anyway? So that's really kind of the difference between a prescriptive-based system and a performance-based system. And so I say the prescriptive is very good for the regulators because it's easy to determine by looking at the drawings if the design complies with the regulation. And they allow engineering, but it's by exception, and it's a little bit difficult if you want to do a very unique design because not all buildings look like a box. Performance focuses on what you're trying to achieve with the building, not specifically how you do that, and it gives the engineer and the architect more flexibility, but it's very difficult for regulators and the fire service to determine, did the design actually achieve the objectives? So each system has benefits and detriments. So for the past 2 years, I've been going around the world looking at how, in particular, the performance-based building regulatory systems have been working in 7 different countries. And I've been talking to regulators, fire service, architect, engineers, trying to really get a sense of what is working and what is not working, and what we might want to look at differently into the future. So I'll go through a few of the countries briefly. I know time is short, so if I start going long, somebody can start waving at me and say stop. But to start with, Australia has the Building Code of Australia, which was implemented in 1996, and that's a performance-based document. And they have this combination of goals and objectives, but they also have a very prescriptive deemed to satisfy component. And if you're going to do engineering analysis, they have this document, the International Fire Engineering Guidelines, which lays out a process for how you identify the objectives of the building, how you develop fire scenarios, quantify design fires, conduct analysis for smoke and fire spread, and also look at, they even have a fire brigade response model within that International Fire Engineering Guidelines. So within Australia, fire safety engineers are required for design, but they're only required to be licensed by law in one state. And so this makes it a little bit challenging, because if you don't have the legal infrastructure to define what competencies the engineer should have, that can allow for bad practice in reality. Another issue that Australia has is that they allow the use of private certifiers. This means that the government doesn't do the approval like City Hall. A private entity can be contracted to conduct the review and certify the building. In theory, the idea was that it would reduce the cost. In practice, if it's an unethical reviewer, they can pick design engineers that they want to and actually not do a very good design or an appropriate review. So you have to be really careful when you do private certification, because the oversight and the ethics need to be very high. So we saw earlier a picture of the Grenfell Tower in London that happened just this year. But 3 years ago in Melbourne, Australia, there was the La Crosse building fire, which had the same combustible exterior facade. They were lucky that no people died in that fire, but the Victoria Building Control Entity did an audit of 151 buildings and found that 51% did not comply with the building regulations. And they saw this as a potential issue with the private certification and what could happen if you're not careful about having good oversight. So as a result, now, following Grenfell, all across Australia, there's a review of all tall buildings and any buildings with combustible facade, but also trying to determine what is the real expected fire safety performance of the buildings. And the fire safety engineers recognize this, and there's a few comments here. I hope you'll get the slides so you don't have to try to read everything. But the engineers recognize that there's no regulations to require building owners to maintain their buildings, to require annual inspections, to make sure that the fire safety management is correct. And so that's an important issue, that you can do a very good design as an architect or engineer, But if the building owner doesn't maintain the building according to the design, then you have no guarantee of the performance expectation. Also, Australia does not have a good set of fire statistics. The fire brigade stopped reporting statistics about 10 years ago. It's very difficult to really understand how large the fire safety problem is or what the particular components are without good statistics. So this is something that should change, and in Brazil or any country, you want to know what's happening, because when you have the data, you know where to focus your resources. So the Australian Building Codes Board, moving forward, is changing their building code. They're keeping it performance-based, but they're setting a single metric of risk to life as the basis for performance. And in the future, fire safety engineers will have to demonstrate that they're not exceeding a particular risk to life level with the combination of materials that they put in the building, and the building owners will have to follow that as well. So I'll switch now to New Zealand. New Zealand has a performance-based building regulation since 1992. They also have this fire engineering guidelines, but also recently they developed a verification method which has more detail for fire safety engineers and for reviewers to follow. So just a little bit of background. In the early 2000s, New Zealand had a very big problem with moisture control in buildings. And so they had a lot of moisture coming through the exterior facade, causing rot within a lot of the timber construction. That led to about a $2 billion impact on the New Zealand market. So the government changed the regulations and really wanted to focus on better quantification of performance, licensing of professionals, audits of the regulatory authorities, and more to try to get some oversight. And as part of this change to more quantification, they developed a fire verification method, which is based on different risk groups and different building uses, but has defined fire scenarios that the engineer has to use, a defined fire size, and even very specific modeling parameters. So I'll just show a few of these things. But this, for example, is the heat release rate curve that a fire engineer would have to use when demonstrating that a building is safe. And it's a little bit hard to see, but it shows more or less a medium t-squared fire growth rate up to a steady state burning. And for most buildings, they require a design fire of 20 megawatts. So that's a very significant fire. If you think about a standard sofa burning in a residential living room, that might be about 3 megawatts. So the fire size that you have to test the building is much bigger. And if you're in an industrial facility, you have to use a 50 megawatt fire. And the reason for this is that you're testing the performance of the building and you're testing your fire safety design. If you use too small of a fire, you don't get an indication of what could happen if those systems fail. Fire safety engineering design also uses quite a bit of computational fire modeling these days. And so this design guide is also telling you what the fire growth rate should be, the production of things such as carbon monoxide, carbon dioxide, soot when you're predicting the smoke movement, even things like the radiative fraction, which impact burning rate, and again, the heat release rate. So the idea is to be very specific on the load that the building is expected to withstand in the case of the fire. And for structural analysis, you have to do a full building burnout. So you have to show that the building will withstand the fire based on the analysis, or you have to default to basically a 4-hour fire resistance construction. So it's really intended to put a lot of control. Now, some of the industry thought it was too much control, and they pushed back a little bit. So the government has modified a little bit to the point where the verification method is used for most buildings, but if you have a truly unique design, you can do fire engineering from first principles, but it's a much higher review process that you have to go through. And they also had some issues with tall buildings, but I'll talk about tall buildings more this afternoon. So one of the other kind of attributes, the government is doing a lot of work to try to address some of these concerns, but the third bullet point, similar to Australia, there's no requirement for a specific fire engineering qualification. And they see this as a problem because anybody can call themselves a fire engineer, and the market generally doesn't know how to accept qualifications, and they can get a bad designer. So this problem of lack of qualifications is a problem in New Zealand as well as Australia, and they're looking at mechanisms such as licensing, but also a central review body with qualified experts to look at some of these very unique designs to make sure that the quality control is much higher. Moving on to Scotland. Scotland has what they call a functional building regulatory system, which is essentially the same as performance, where they have functional statements in the regulation, and then they have technical handbooks, which are more or less the prescriptive, deemed to comply type of documents. For fire engineering analysis, most engineers follow British standards, so BS 7974 and BS 9999. Part of the problem is that the BS 7974 in its 8 parts is very detailed, which is very good. But the authorities are finding that many of the engineers are not following the guidance in total. So they write a statement saying, we followed the principles of BS 7974, but when the fire services and the building authorities review the design, not all the components are there. So it's really not appropriate to say you're following a specific standard or guidance if you're not following it in total, because it's there as a package to make sure that everything is working appropriately. So there is some concern that even though the regulatory system is functional or performance-based, it's really being interpreted as prescriptive. And part of this is because the local authorities look to the technical handbooks as the first base instead of allowing initially the engineered design because they don't trust fully the engineers. So they make the engineers demonstrate the differences to the technical handbooks. So here again, we have this challenge with the qualifications of the engineers, but there's also an issue with having appropriate qualifications for the people reviewing and approving the designs needs to be at that same level to have confidence that the design is actually meeting the objectives. So Scotland right now, as a result of some of the work that I did a year ago, is looking at developing qualification system both for engineers but also for the local authority verifiers. And so it's probably going to follow the Institution of Fire Engineers, Chartered Engineer status, both for the engineer and the reviewer. But in England and Scotland now, even though you can become a chartered engineer, it's not required by law. And again, that's the big difference. If a client doesn't understand how to recognize the benefits of a chartered engineer, they may just hire somebody that has inappropriate qualifications. The Netherlands has had a performance building code since 1992. They have a large focus on developing innovative solutions, and unfortunately, fire safety engineering is not very well developed. There's no university programs in fire safety engineering. They have a lot in civil engineering. They have this big challenge of keeping the ocean from flooding their country. So the civil engineers are very strong, and they've done a lot of work with probabilistic methods. So now the fire safety engineers are thinking, because we have all this knowledge on probabilistic design due to flood, can we bring that in to have a probabilistic design for fire safety? So where other countries are using a more, what I would call deterministic or process approach, in the Netherlands they're looking at following more of the structural reliability or probabilistic approach to design, where you look at the objective is focusing on life safety. You have 3 different risk levels for buildings, and you have a probability of occurrence of event and safety to life that would be the guidelines for the design. So this is the current approach that they're developing. I'm not so sure that they'll implement it anytime soon, but it's a rather interesting approach. Sweden has had a performance-based system since 1994, and with their initial regulations, it was very open. It didn't have much guidance, and that caused a lot of problems in the market because there were different interpretations by engineers, by the regulators, and others. So in 2011, Sweden changed their building regulation and put more specific requirements on the design fires as well as the acceptance criteria, very similar to what New Zealand did. So there's a document called the General Recommendations, which deals with verification of design, and there's 3 approaches that they allow. A qualitative assessment if it's a very minor design, a scenario-based analysis similar to New Zealand, or they allow a quantitative risk analysis. And so I'll just talk a little bit about the scenario-based approach. So similar to New Zealand, it gives you fire growth rates that the engineer has to use, heat release rates, and fire load so that you can look at the initial stage, fully burning, and post-flashover fire. What's interesting here is that the heat release rate is 5 megawatts. If you remember, it was 20 megawatts in New Zealand. And so there's a different philosophy in terms of what the size of the fire should be in terms of testing the building. So if you look to develop a design guide here, that would be one of the big factors that I think needs to be looked at. Here's an example of some of the criteria that they use. There's a defined smoke layer above the floor, so you have to have at least 1.6 meters of clear height, plus 0.1 the height of the ceiling. So as the ceiling height adjusts, that level adjusts. There's different visibility requirements, 10 meters in a large space, 5 meters in a smaller space, maximum radiant heat flux that people would feel on their skin, and things like that. But it's very good if you're going to do modeling to be able to demonstrate what you think the fire is actually going to do in terms of impacting people as well as impacting the building. So some of the observations from the engineers was that the change in guidance has been very helpful, but they see another problem. And Sweden has a very long history of fire safety education. Lund University has been graduating fire safety engineers for about 25 years. So the problem that some of the engineers, particularly the older engineers, are seeing is that the young engineers are very good with computer modeling, but they have no idea how to engineer a good design. And they're used to computers because they play computer games, but they don't understand how to interpret the output in relation to what makes a reasonable design, and they come up with impractical designs. So here's a case where technology, which can be very helpful, if not properly applied, can end up with a design that's even worse. So there needs to be some controls. And if you get the presentation, this is just a link to one of the reports that I had written for Sweden. Briefly on Spain, they have a performance building code as well. The Performance Act was initiated in 1999, and the technical building code was published in 2006. A problem there, which as I understand is a similar challenge here, is that fire safety engineering is not recognized, like architecture or civil engineer. And there are no fire safety engineering programs. And there's no requirement to use fire safety engineering. So they implemented a performance regulation, but they didn't have any fire safety engineers qualified to do it. So it's a rather mixed up kind of place. And then briefly on Japan, Japan is different than the other countries I looked at in that they have separate building regulation and fire regulation, the building standard law and the fire service law. And the fire safety requirements are split between the two regulations. So in the building standard law, you get things such as structural safety in case of fire, and you get evacuation. But the fire service law deals with active systems such as sprinklers and detection systems. So that requires a lot of coordination between the building regulations or the building regulators and the fire service, because you have to look at both sets of regulations depending on what aspect of building fire safety that you're controlling for. So if you're dealing with fire resistance, smoke control, and evacuation, that's building standards law. If you're talking about sprinkler system, detection, communication, fire service, support systems, that's the fire service law. And so in a design, all of that has to be very well coordinated, which doesn't always work. The other aspect about Japan is that they have 3 different methods for verification. One is that you can just follow the prescriptive option in the code. The second one is you can follow what's called the ordinary verification method, which is very specific relationships between smoke filling and evacuation, or specific requirements for structural engineering design. Or you could go to a full performance-based design. If you take that last route, you have to submit your design to a panel of experts, and the panel of experts that's put together through the ministry and approved bodies will do a complete review of the design. And that level is typically academics and researchers. So a short summary of Japan is they have a performance code, and they have what I call the medium level verification method, but that's all based on kind of 2-zone models and simple equations. If you want to do a full performance, you have to get ministerial approval, but it's difficult to get that approval. So there are a variety of challenges, and with that long time to approval, fewer people do the full performance because of the uncertainty in the end. So to try, I know I'm going quickly, but I'm trying to get everything in here a little bit. One other thing that I did after going to the countries was to post a survey online through SurveyMonkey. And I asked engineers around the world, I think I had a few engineers respond from Brazil. I had 400 respondents in total. Most of the people were from Australia, New Zealand, Sweden, Scotland, US, and Spain, because those were the countries I visited. But if we look where people are doing actual fire safety engineering, I know it's difficult to read, but the first bar is to protect people. So life safety analysis was the primary means for doing fire engineering, and the second primary area was property protection or structural protection. And then if you look at the methodologies people use, because it was life safety, the most is what we call ASET, RSET, which is available safe egress time compared to required safe egress time, with the second most analysis being around structural stability in case of fire. It was also interesting to see a fair number of analyses related to the fire brigade. And this is important because in many of the countries there's a requirement not only to protect the safety of the occupants, but to provide reasonable protection to the fire service while they're undertaking rescue and suppression activities. And so that's where structural stability and fire brigade operations analysis becomes important, because you can't just design the building with enough time to get the occupants out and then let the building collapse on the fire service. You have to design the building to allow the fire service to undertake their operations. So I think that's a very good part that is built into some countries that is really important to consider. I apologize, this is impossible to read the detail, but the next few slides are just percentages of different aspects in the design. So this is asking in different countries, what is the way that you mostly undertake your design? So the blue is in compliance with the prescriptive or deemed to comply, and the purple is doing more performance. So you can see in Spain, it's mostly prescriptive in Scotland as well. And then if you look at the green and the purple, in the US and Australia, much more engineering analysis is undertaken. So it's interesting to see how that differs from country to country. This is just a snapshot of the different engineering standards that countries use, and the detail isn't important, but you can see by the distribution of color that there's no uniform single approach to fire safety engineering that's used around the world. That's problematic, because if we had a more unified system, then we'd be much better getting understanding, education, and compliance. This was an open question of what is your general sense of the state of performance-based design for fire in your country. In this case, the blue is very good and the red is good. So Australia and New Zealand thought things were pretty good. The green, yellow color is bad and purple is very bad. So you can see Scotland thinks things are mostly bad and Spain thinks it's really bad. So some of this is a function of, if you don't have requirements for qualifications of engineers and all the support mechanisms, even if you have that type of regulatory system, you can't work with it. So you have to put everything into place if you want to have this type of an approach. Probably the most interesting outcome for me is this one. Do you think there are enough qualified fire safety engineers in your country? Overwhelmingly, no. And these are all countries that have been doing fire safety engineering for 20 or 30 years. In every one of them, more than 75% don't think they have enough engineers. So if you're starting to go to the area where you're going to have education for fire safety engineers, you got a long time before you're going to have enough. And so this is just another point of caution in terms of, how far can you go, how quickly, to make sure you're delivering a good level of safety in the environment. And these are just some breakdowns about whether or not you have enough qualified engineers. And in all countries, even the US, where we've had fire safety engineers for 50 years, we don't have the capacity to meet the demand of the market, both in the design and in fire service and building control. The disturbing part is that about 75% of the respondents think that non-qualified people are undertaking fire engineering designs. And this is the problem when you don't have a good qualification system, because it's that type of situation that leads to buildings that have problems like Grenfell and others. If you don't have the right qualified people doing designs and review, you don't have a good fire safety management culture, you can get into very difficult challenges. So here the US thinks they're doing a little bit better. Australia is really concerned about how many unqualified people are undertaking designs, at least in the determination of the market. And this is a similar graph of, what do you think in terms of, are the people reviewing the designs qualified? The blue colors and the red colors are bad, they're the low end. So again, it's no surprise Scotland and Spain that had the big situation or concern with the quality of engineering also has the biggest concern with the quality of review and approval. And in this graph is, do you have a legal or professional mechanism for qualifying fire safety engineers? Spain and Scotland mostly no, Australia and New Zealand mostly yes, but the yes part is becoming a chartered engineer, but that's still not legally required. So there's a difference between professional qualification and licensing. And I think this is the last survey question. Across all countries, a large majority of people think that specialty certification for things such as computational fluid dynamics modeling, finite element analysis modeling, evacuation modeling is required. Because just because you get an engineering degree doesn't mean you know how to properly run a model in a fire environment. So having specialized certification to enhance the education is important. And again, this is reflecting which countries have no certification. In Spain, it's very clear that there's no mechanism for recognizing fire safety engineers. So a few summary observations. Every country I went to has had a performance-based building regulatory system for a number of years. I expected to see a lot of performance-based design being done, but mostly it was still following the prescriptive or deemed to satisfy solution. And a large part of that was that the market didn't think they had enough qualifications, and there's not enough educational programs to develop competent engineers and practitioners. So across all countries, somewhere in the range of 5 to 10% are performance-based fire safety engineering design. Maybe around 10 to 20% are deviations from the prescriptive requirement, and 70 to 80% of the time, they're just following the prescriptive code. And there's a lot of reasons for that: inadequate measures in the code, but inadequate number of engineers and reviewers, and a not very good review process. So I kind of asked myself, if we've had performance-based regulations for 20 or more years, how can we haven't advanced further with fire safety engineering and the performance concept? We have the performance, but it's not quantified. So if you don't have clear quantification of the acceptance criteria, the scenarios, and the fire, it's hard to design. That gets more complicated when you don't have the qualification systems for the engineers. And if you don't have the education to qualify the engineers, then you just have a really big problem. So for some of the countries that have had the situation for a number of years, I find this graphic from the technology industry very interesting. So basically what this says is that some type of new technology or innovation occurs, and everybody jumps on the bandwagon. Everybody wants to use it. Performance-based design is great. We're going to adopt it. And then you start to find out what it actually takes to do that. And you start to get disillusioned with the actual time it takes, the cost, the recognition, and so forth. So you fall into this trough of disillusionment. And then you have to kind of claw your way up the slope of enlightenment when you find out how much infrastructure you have to put in for education, training, competency, certification, until you get to a level where you're working productively. So I think we are now, in many countries, kind of moving up to a steady state, but it's taken many years to really determine all the shortcomings and how much infrastructure and education and training is needed to make the system work effectively. So moving forward, many countries are taking steps to add more quantification into their performance codes to help deal with these issues. They're trying to get more guidance around the qualifications of the practitioners in the market. What is the minimum? How should licensing happen? How do we determine competent participants? Some of the more progressive countries are trying to go further and say, we're worried about risk to life. We'll make that the fundamental unifying criteria. So that's just going to mean more education is required as we move along. So going forward, for me, it's very clear we need more university programs producing people at all levels, engineers, qualified technicians, authorities that understand the concepts and how the engineering works together. We need better definition of the qualifications and competencies of fire safety engineers and what their expectations are relative to building design. And we need to define all of these components so that I have the same interpretation as everyone else to avoid confusion. I think eventually we'll go to more risk-based methods, but that's probably another generational shift. So I need to thank all the different governments and sponsors who sent me around the world to do some studies. Thank you very much to Professor Ono and to the group here for inviting me. And I thank you for your attention and would be happy to answer questions when we get into the session. Thank you.